I'd like to introduce our final speaker, Dr. Slava Turyshev. He is a physicist and research scientist at the Jet Propulsion Laboratories in Caltech, and also a professor in the Department of Physics and Astronomy at UCLA. And he'll be giving us a talk on fundamental physics research on the lunar surface. So, welcome, Slava.
Excellent. Thank you very much. Good afternoon, everyone. So, in this presentation, we will talk about relevance of fundamental physics for the research on the moon, and really will cover the science objectives and also the technologies that are being developed and will be deployed on the lunar surface and in lunar orbit that will enable not only the science exploration of the moon, testing fundamental physics theories, but also to enable transition to the lunar environment and then next to Mars. Before I proceed, I will cut my video so it will be better to go. Next chart, please. Next chart, please. Excellent. So this is a little summary of what to expect in the near time frame. So realistically, there is unprecedented number of lunar missions. We have a significant lunar traffic with more than 40 missions planned, including 68 space vehicles, including sort of involving many national space agencies. It's very important to note that there is a very prominent presence of private space industry, including SpaceX, Moon Express, Astrobotics, Blue Origin, Sierra Nevada Corporation, Marston Space Systems, and many others. There are multiple emergent trends in cislunar activities. We have a significant emphasis on lunar surface exploration, with more than 16 missions are going to be deploying lunar lander, rover, or both. So there is emergence of lunar relay orbiters. At least 4 missions are planning to deploy lunar relay orbiters to serve landed vehicles and serve as navigational beacons. There will be many CubeSat and SmallSat missions. There will be mix of crewed and robotic missions, both in orbit and the lunar surface. So there will be multiple commercial landers to deploy science instruments and technology demonstrations on the moon. There is a major technology advancement and science opportunities are expected. So there is emergence of long duration sensor networks on the moon, on the lunar surface. There is increased interest for lunar far side, with quite a few landers and rovers on the rim of the South Pole and actually on the far side of the moon as well. So there is opportunities for optical in the near side and radio on the far side telescopes for astronomy and cosmology. So this is very interesting developments that are ongoing, and it's really the field that is really going to be happening in the very near time frame. And really the emphasis is, how do we benefit from this? What fundamental physics role in these activities, and how fundamental physics will benefit from this, and also how this area will contribute to the lunar exploration. Next chart, please. I will begin with talking about lunar laser engine. Lunar laser engine is a really legacy of the Apollo program. In Apollo 11 deployment of lunar cornucube arrays in 1969, and you see the left bottom picture here is Buzz Aldrin carrying on the left the panel of cornucube reflectors, which were deployed on the lunar surface. And so in Apollo 11 initiated shift from analyzing lunar position angles to ranges. The present day accuracy is roughly about 5 millimeters, limited by Earth atmosphere. You can imagine that we measure distances between Earth and the moon to the very small number, less than a centimeter, which is unique. Then you see lunar Apollo 11 lander, Apollo 14 cornucube reflectors. The panels between are similar between Apollo 11 and Apollo 14, are similar cornucube panels. Apollo 15 is a little bit larger. You see sets of cornucube reflectors on Apollo 15 panel. It's about 300 reflectors. They're about 3.8 centimeters. And the benefit of those cornucube reflectors is that when you shine a laser light into them, the light is being triply reflected from the edges of the cornucube. It comes back exactly in the direction it came from. So this is very useful for measuring distances, propagation distances between observatories on the moon, on the Earth, and the cornucube reflectors on the moon. On the right top panel, you see 5 corner cube reflectors, panels of reflectors are being now deployed on the moon within the course of Apollo 11, Apollo 14, Apollo 15 missions, and also Lunar 17 and Lunar 21 Russian missions that were deploying 2 lunar rovers called lunokhodies. And lunokhodies carried French-built panels of corner cube reflectors. Over the years, the precision with which we range the moon essentially changed from roughly 20 centimeters to now less than a centimeter. And RMS residuals are at the level of roughly 15 millimeters. And we need to move down to 1 millimeter because this precision opens a very significant area to test fundamental physics. Next chart, please. In the next chart, you see how those ranges were evolving through time. On the top chart, you see from 1970s all the way to roughly 2020, how many normal points were collected each year and which stations actually used to do this. So there are multiple stations on Earth that are involved in lunar laser ranging. This is truly international community. We began the lunar laser ranging with using McDonald lunar laser ranging operation. Then French-built observatory Côte d'Azur joined the list of stations, and actually it's a very productive station. Recently moved from working on green laser, now working in infrared 1064, and essentially you see that observatory Côte d'Azur provided a lot of normal points in recently in infrared band. So there are multiple other stations throughout the globe, several stations in Europe and in Africa, and so many more stations are being built. This is very exciting development now because we have multiple activities, ongoing activities on the moon and actually on the ground. The top right chart, you see statistics of ranging different corner cube reflectors. As I mentioned, there are 5 corner cube panels, and until 2019, Apollo 15 was the most ranged reflector, and it has roughly 67% of all the normal points. But after introducing infrared capability on Apache, on Observatory Côte d'Azur in 2019, there's pretty much even coverage of several reflectors. And so going forward, we'll expect to have pretty much similar coverage of those reflectors and the new ones that will be deployed on the moon. Nevertheless, there are some selection effects, and the bottom chart shows that there's very few normal points acquired during new moon and during full moon. So in the transition, you have many more points, but really the challenge is actually get the data point from new moon and full moon, because that actually will enable us to improve the tests of general relativity and studying lunar interior. That the bottom right chart shows the historical evolution of RMS residuals, where we use the normal points collected by the lunar laser ranging operations internationally and actually fitted with the model that is very elaborate model, not only the distance, but rather lunar interiors being also carefully modeled and included in the model. So the present day normal points are fitted with roughly 15 millimeters precision. Next chart, please. This data is used to make major advances in the tests of general relativity. One of the cornerstone principles in general relativity is the equivalence principle. Equivalence principle states that gravity is really agnostic towards the composition of the body. So when gravity couples to any object, it should be immune with respect to body's composition. And so realistically, what we are doing, we are dropping the Earth and the Moon in the gravitational field of the Sun. And so if the equivalence principle is not violated, the orbit of the Moon around Earth should be very well predicted. And you see the chart on the top right chart, so the orbit will be very well predicted. But if the equivalence principle is violated, we do expect polarization in lunar orbit, and so the size of this polarization will be roughly 13 meters. And so the orbits of the two bodies, the Earth and the Moon, will deviate by 13 meters. And as I mentioned, so we measure this orbit of the Moon with a precision of roughly 1.4 centimeters. And so we have not seen this effect. And so that enables us to test general relativity to very high precision, and especially the violation of equivalence principle recently was tested at the level of roughly 2.4 times 10 to the minus 14, which is the difference in accelerations of Earth and the Moon falling in the gravitational field of the Sun. So this is very good precision because compared to the spacecraft tests of weak equivalence principle, which were recently conducted by the French-built microscope mission, we are reaching a similar precision in terms of uncertainties. So the microscope precision is roughly twice less than the lunar laser engine, opening a very significant exploration area for us in the near future, because we definitely can move into this region and actually improve the precision by quite a few orders of magnitude. Strong equivalence principle, which is actually includes now not only the body composition, but actually the contribution of gravitational energy into the equivalence principle, was tested by the lunar laser engine data to roughly 3 times 10 to the 4 3.4 times 10 to the minus 4, which is extremely good precision compared to the previous data. Several parameters, relativistic parameters, were tested independently, like parameter beta, which measures nonlinearity of gravitational superposition. And so this is very interesting parameter because we are really testing the regimes at which gravity may fail, and or the general theory of relativity may fail, because we are posed with very significant challenges from cosmology. For example, the presence of dark energy and dark matter in the universe and in the galaxies, spiral galaxies, alludes to the possibility of the breakdown in general relativity. So lunar laser engine can test those theories that actually were predicted to explain those the puzzles in astrophysics and cosmology to very high precision. And so one of the recent tests of possibility that gravitational constant is not a constant, but really varying with time. So the G dot over G was measured to roughly precision of 10 to the minus 14, just shy of that 10 to the minus 14. And realistically, that implies that the gravitational constant evolved less than a tenth of a percent during the entire history of universe, which is a very strong conclusion and actually helps to improve our understanding of cosmology on various scales. So lunar laser engine is extremely relevant experiment and should be continued, because now we are benefiting not only from the instruments, but also from the long duration of the data span that covers from 1970 to the present and going in the future. Next chart, please. So improving the precision with which we can take normal points of using lunar laser engine actually contributes quite significantly to our tests of to our ability to test general relativity. In this case, even a millimeter precision, which we are very close to, will enable us to improve the tests of weak equivalence principle, strong equivalence principle, and test variability in the gravitational constant. But we are aiming now at 0.1 millimeter, which is possible with the technologies that are already being deployed on the moon or being developed. So with this, we will be definitely working in a very new regime. And so within the next 5 to 10 years, we should be able to approach very impressive limits with which we can test possible deviations from general relativity and test theories for cosmology and astrophysics that were proposed to explain dark matter, dark energy, those phenomena that actually are quite puzzling. But not only that, lunar laser engine is extremely relevant to conducting lunar science. With lunar laser engine, we can precisely position the positions of the Copernican reflectors on the moon. And by doing that, we are studying lunar interior. So we can identify positions of the moon, of those reflectors to less than a centimeter level. And so low degree gravity field is being distinguished from mantle and the core. But the most exciting part is that we are now sensing the core, the lunar core. As you know, there is a liquid core inside the moon, which is roughly 420 kilometers. And so there is a solid core inside of roughly 60 kilometers in diameter. So lunar laser engine indicates the composition of the moon and actually will enable us to talk more, to get more data on the lunar interior and study the composition of the moon and the history of the moon, which is extremely relevant to our studies of other celestial bodies such as Phobos, Deimos, as if we plan to go to Mars. So this type of research is extremely relevant. But besides that, lunar laser ranging is very important to establish a lunar reference frame. It provides three-dimensional orbit orientation of the moon in the inertial frame defined by international coordinate reference frame. It allows to establish positions and on the moon and navigating spacecraft around the moon, which is extremely important for the upcoming activities with respect to Artemis program, and essentially will help to position a lunar lander on the surface to very high precision. And so lunar laser ranging is used to determine orbit orientation of the moon as a function of time, which is extremely important. And so anticipating an ongoing developments, we look for new cornicube retroreflector instruments to be deployed on the moon within the CLIPS program. And so not only the passive instruments will be deployed, but also active optical transceivers will be deployed on the moon, which is extremely exciting. And also there are some facilities that are being built on the moon, which on the Earth, which will help us to improve tests of general relativity and to conduct studies of the lunar interior. And I will talk about one of the, yes?
You have 5 minutes, Slava.
Excellent. Next chart, please. So next chart. So one of the facilities that I'd like to highlight is the facility on the Table Mountain Observatory in California. We are using here 1 kilowatt laser, which is roughly 200 times more powerful than the laser that are used on other facilities. With this type of instrument, we are able to conduct very exciting research. Next chart, please. So with the 2 kilowatt average power, we are able to reach precision of roughly 30 micron, which is differential range precision, and focusing on lunar interior. With this type of facility, we can conduct studies of the moon, tests of general relativity to very high precision, much better than currently possible. Next chart, please. So by switching between different cornicubes on the moon, we initiate a very new observable, which is difference laser ranging, which is limited only by Earth atmosphere to roughly 30 microns. And so now our emphasis will be on the lunar interior in addition to general relativity. So we are getting very significant flux from the from the cornicube arrays already on the moon. We're getting roughly 10 to the fourth photons per second. This is flux which is quite different compared to single photon detection that is done by other stations on Earth. Next chart, please. So with the lunar laser engine that established on the Table Mountain, we are now talking about actually transmitting power to the moon. So we can deliver up to 5 kilowatt power on the moon by using high power lasers, arraying them in small arrays on Earth. So essentially, we are thinking about putting in a small array, which is roughly 50 to 100 small ground-based telescopes, each of them like 30 centimeter in diameter. With this type of array arrayed in 10 by 10 telescopes, we can deliver up to 5 kilowatt power, continuous power on the moon, which is quite exciting because now we can deliver power and allow for multiple instruments to sustain lunar nights. Before any nuclear power will be deployed on the moon, but lunar laser ranging and essentially high power opportunities allow us to really deploy very interesting opportunities for the moon and to allow for survival of instruments on the moon. Next chart, please. So once power on the moon is available, we can conduct multiple other experiments, such as using radio beacons on lunar landers. We can conduct same beam interferometry and VLBI Delta Door experiments, as those were done by MIT in 1970s and JPL by the same time, looking at the radio beacons from ALSEP packages on the moon, essentially, and observing them on the background of extragalactic quasars. So this is extremely powerful because this technique will allow us to reach similar precision to lunar laser ranging at roughly few millimeters precision. This is a new technique that is emerging. Next chart, please. And so also lunar radio ranging, once we have beacons on the moon that are capable, sort of the landers on the moon with very precise transponders, will allow us to conduct ranging to those landers on the moon. And the lunar radio ranging can be done with a few millimeters precision, and essentially similar science compared to that of lunar laser ranging will be able to be studied. Next chart, please. And so once we do that, essentially lunar laser engine and lunar radio engine are complementary, because lunar radio engine, you can range through lunar full moon and new moon. Essentially, that will allow us to have a continuous coverage of lunar assets. So in addition to that, same beam interferometry and inverse VLBI methods will be extremely powerful, because now we have radio sources with continuous power, and we should be able to reach similar millimetric precisions. And all of this will be helpful to study the moon, to establish reference frame for navigation and navigation in cislunar activities. Next chart, please.
Slava, you're coming up on 1 minute, so if you
Excellent.
can please wrap up. Thank you.
Almost there. Next opportunity will be optical transceivers, which will allow us to reach even higher precision range in the moon. Optical transceivers will be deployed for communication and navigation purposes. Next chart, please. And so the precision that we're able to reach with optical transceivers are in the sub-millimeter and a micron level. So this is quite unique. That will be very helpful for navigation and fundamental physics. Next chart, please. So what is to expect in the near future? The anticipated developments, we have the CornerCube arrays being deployed on the moon as NGLRs with the dark Curie being the PI. So there is a solid single CornerCube is being deployed. Masten PNT beacons, position navigation timing beacons, will be deployed on the moon to enable early development of the radio techniques. Emerging opportunities, we have laser to optical transceivers on the moon. There may be clocks on the various constellations. There will be high precision laser range and navigation from TMO, and also power delivery to the ground-based arrays to the arrays on the moon. That will be quite an important development. So next chart, please. And this is my last chart. Essentially, once the power, dust, communication, thermal issues are addressed, I guess then the astrophysics and planetary physics and heliophysics will have a renaissance from the moon, because we can do a lot of interesting studies in terms of planetary sciences, search for near-Earth asteroids, monitoring the entire environment around Earth, study heliophysics, space weather network on the moon. And the most interesting, I think it's a far sight when we will deal with cosmology and astrophysics, studying evolution of the universe in 21 centimeter, because 21 centimeter radio essentially is being quite polluted on the ground. But on the far side of the moon, we can do a very exciting science, really touching the beginning of the universe after Big Bang. So this is exciting science, and we are looking for emerging opportunities and to conduct science from the lunar surface. Thank you very much. This completes my presentation. Maybe next chart for fun.
Very nice. Well, thank you, Slava, for that wonderful talk.